Okay, so I had to cut that last video short, but let's pick up where we left off. So I actually worked a little bit ahead. I think we left off on this line though in that last video. So we kind of did that trick that I said is used a lot in calculus, adding something and then subtracting it away, making this expression much more complicated than it looked in the previous step, but it gave us something to factor out of different groupings of terms here. And so now what we have in each set of parentheses is a place where we can use a Pythagorean identity. Cosine squared of y plus sine squared of y. Sine squared of x plus cosine squared of x. Each of those is equal to 1 by our Pythagorean identity. And notice that simplifies way down in this next step. Cosine squared of x times 1 minus sine squared of y times 1. And then to end this proof, multiplying something by 1 doesn't change it, so this really comes down to cosine squared of x minus sine squared of y. That's what we were trying to prove in the first place. Okay, so definitely a tricky identity because that one step going from here to here is not an intuitive step at all. It's kind of, you have to see it done before you would think to do something like that. All right, we want to look at one last little topic here. It's an application of the difference identity for the tangent function. And what this has to do is finding the angle between two lines that have been graphed in the plane. So before we jump into that, there's a concept that we need that relates to the tangent of an angle that a line forms with the x-axis and the slope of that line. So suppose we're looking at a line that has been graphed in the plane. This is that line right here, okay? And we know that the equation for a line in slope-intercept form looks like y equals mx plus b. And this equation is not terribly important except for that m there that represents the slope of our line. Now I know that the slope of a line can be evaluated also by the rise over run idea. You pick 2 points on that line, say here and here, and you determine as I go from one point to the next, how far do I move to the right and how far do I move up. We call that rise and we call that run. So the slope, which is m in this line, is equal to rise over run, which would look like a over b, given how I labeled these sides here, okay? But if you notice, rise and run, if I think of those as actual line segments, together they form a right triangle right here. And what is the tangent of this angle theta that the line forms with the with that line, or sorry, with that x-axis there? Well, tangent of theta would be opposite over adjacent, which is also a over b. Tangent of theta. So what this tells us is that the tangent function in particular is directly related to the slope of a line. In particular, the tangent of the angle that a line makes with the x-axis will equal the slope of that line. We use that concept over here, where what we're really trying to do is find the angle between two lines. So we're going to say that we have two lines in the plane, L1 and L2. And notice where these are graphed, they intersect at a point here. And then this theta right here is going to represent the angle between those two lines, okay? Now, in addition to that angle theta, I'm also going to assume that we know the angle that L1 makes with the positive, or with the x-axis, and the angle that L2 makes with the x-axis. My description gives different labels for these. So in my description, I'm calling the angle between L2 and the x-axis theta 2. So I'm going to change that label here, and this would be theta 1. Okay. Now using this picture is a little bit small, so I'm gonna magnify the part that we care about. You notice that these two lines, the blue line, the red line, and then the x-axis, form this little triangle right here. I want to look at that triangle. It's kind of like this. Okay. So first of all, one of these angles we know, it's theta 2. Okay. Now if you notice, theta 1 is out here. But theta 1 plus this angle right here go together to form a straight line. That means that these are supplementary angles, which in other words would mean that they add up to 180. But if that's the case, then this angle right here would be equal to 180 degrees minus theta 1. Okay, that way this angle and this angle will add up to 180 degrees. What can I say about this third angle up here? Well, looking at the diagram, that angle, this requires you to remember a little bit of geometry, but this angle is vertical to this angle. We call these vertical angles when they're diagonally across from each other from these two intersecting lines. Vertical angles are always congruent, and what that means is that if this angle is theta, then this angle should also be theta. So that would be theta as well. Okay? Now those three angles, theta, theta 2, and 180 minus theta 1, form the three angles in a triangle, which means they should all add up to 180 degrees. So with that said, let's do a little bit of work with that. So here we have the sum of those three angles, theta 1 plus 180 degrees minus theta 2. Actually, I think I'm using the old labels here. Let me fix that. Theta 1, that's theta 2. This is theta 1, theta 2. Doesn't really matter. We end up with the same result either way. So if we were to simplify this and solve for theta in this equation here, the 180s on each side could cancel out. I could add the theta 2 to both sides, subtract theta 1 from both sides, and I get theta equals theta 2 minus theta 1. So what that's doing is it's giving me a relationship between the angle that we're looking for, and remember that's the angle between those two lines, and it's equal to the difference between those angles that each line creates with the x-axis. Now, if I were to take the tangent of both sides of this, I would get tangent of theta equals tangent of theta 2 minus theta 1, and there's where I would want to use my difference identity. So doing my difference identity here, this is equal to tangent of theta 2 minus tangent of theta 1, all over 1 plus tangent of theta 1, tangent of theta 2. But remember what theta 1 and theta 2 are. Remember, those are the angles that those lines created with the x-axis. And down here we show that the tangent of such an angle will always equal the slope of the line that created that angle in the first place. So tangent of theta 2 is the same thing as the slope of line 2. Tangent of theta 1 is the same thing as the slope of line 1, which I'm calling M2 and M1 for those slopes. So I can change each of these tangents into an M representing just the slope of those lines. M2 minus M1 all over 1 plus M1 times M2. Okay, so I want to use that little formula that we just came up with, that idea, in an example. And let me get some pulled up here really quick so we can run through this. This example appears in your book, and I'm using it mostly because I can use the picture that it comes with. So what we have here is a climbing wall that's illustrated here. And it's attached to the ground by what's called a guy wire. If you don't know what a guy wire is, you've seen these before. They're cables that are used to provide stability to a tall pole, usually like a telephone pole or something like that. There's two guy wires attached to this climbing wall, which we're going to call R and S. And if you notice, S attaches to the wall at a height of 40 feet from the ground. R attaches to the wall at a height of 47 feet above the ground. Both wires are attached to the same point 50 feet away from the base of this wall. And we're going to say that beta is the angle between, or we're going to label a couple of angles here. Beta is going to be the angle between guy wire R and the ground. Alpha is going to represent the angle between those two wires. So those are the two wires that we want to find the angle between in this problem. Okay, our goal here is to find alpha. So each of these guy wires we can think of as a line. And according to the work that we just did, developing that formula, in order to find the angle between these two lines, we really just need the slopes of those two lines. How do you find the slopes of these two lines? Well, slope of, let's say, S and slope of R, we could just use rise over run in both cases. So what should we say the slope of S is? Slope of S is going to be rise, which is 40, over run, which is 50. Notice that's the height of that right triangle and the base of that right triangle. It's 40 over 50, or I can simplify that to 4/5. Let's call that M1. Okay, and then let's do the same thing with slope of guy wire R. So in this case, the rise is 47, the run is still 50. So I have 47 over 50, which is already simplified. Let's call that M2. Okay, so according to the work that we just did, the angle between these two lines, if I were to take its tangent, so calling that tangent of alpha, that should be equal to M2 minus M1 over 1 plus the product of those slopes, M1 times M2. But what is that equal to? Well, we have M1 and M2 here. So M2, that would be equal to, where'd you go? M2 is equal to 47 over 50. M1 is equal to 40 over 50. Okay, and let's put that over 1 plus the product of those two. Actually, let's call this 4/5. No, I'm going to keep it 40/50ths because then I have common denominator. M1 here, I can call it 4/5 times M2, which is 47/50ths. Okay, what is that equal to? So 47 minus 40, that's going to be 7 over 50 over 1 plus, let's see, that'd be 160, this is 188 over 250. And at this point, you know, you can kind of keep doing the arithmetic, or if you have a scientific calculator, think about what it is we're actually looking for. We're looking for alpha, right? Alpha is the angle between those two lines, and so all we would need to do once we get a value for this is take an inverse tangent. But technically, you could take the inverse tangent of this at any point along the way. So I'm actually just going to leave it in that form. Alpha is going to equal the inverse tangent of 7/50ths over 1 plus 188 over 250. And that's going to be approximately, if we work that out in degrees, 4.57 degrees. That seems to be a reasonable angle looking at this. You can never really trust a picture completely, but in this case, if we do kind of trust the picture, it seems like a relatively small angle. 4.57 degrees is a relatively small angle. I just want to point something out too. You can keep going with the arithmetic here, but again, if your calculator supports doing several operations at once like this, it's fine to take the inverse tangent at this stage as opposed to getting, you know, a single fraction down here. But that's going to wrap it up for this section.